should be operational now. I'm gonna make sure that my mic is projecting properly. Headset microphone. Yeah, that should be it. Okay. So let me see what I can do about finding a way to look at chat so that I can see what you all are currently asking me about. Okay. Gonna switch this mic output real quick to see what it changes to. Do you pick up anything? You still do, so that's a little bit weird. So this and see how that does. Alright, so I'm streaming, I'm recording, and I'm trying to pull chat up so I can watch it and see y'all's questions. Okay, so we should be good to go right now. I'm just going to have a bit of audio issues right now, real quick. Testing to make sure that I can see everything. Alright, I can see the chat room. So let's go ahead and type something in, Lily, so I know that you're here watching. Okay, awesome. And there's not really any reverb from my TV telling me from the chat, so we should be 100%. Disconnect the tablet so I can be in tablet mode. Okay, so in this version, you can see less stuff. So let me see about editing the display so we can see our stuff better. This is crazy. I don't like it. Do the thing, please. Ugh. Okay, let's put this up. And I want to see what you can see. Okay, but if I do it this way, you can see more, right? Yeah, so let me fix the display stuff here. But of course it's going to act silly until I get it working properly again. So give me a few seconds to get this working properly again. Okay, we should be back to a good ratio where we can see everything happening. Alright, let's hide this. There we go. Now we've got maximum calculus window. Alright, I'm going to add some lines to this paper. And what we're going to do is we're going to start at the top. Now that I'm all set here, going into this, and we're all set. This all looks good, right? We're looking good? Ready to do some calculus? Alrighty. Alright, so Lily's question was, and I'm going to get my phone to recall exactly what that question was. Her questions, actually, were, let's go to draw, and we'll say that she had question, right? What is the point of IVT? And my answer is that IVT helps us find the zeros and roots of various functions. Okay? I can do one on Rolle's theorem afterwards. If you remind me after we finish Lily's 2 questions, I will try and find an example about Rolle's theorem for us to do. Okay? So this was Lily's first question about IVT. Lily, does this clear up your question? Kind of. Elaborate on what I need to hit on. Do you need to see a visual of what's going on? Oh, like in what? Okay, I got you. So the revised question is, what is an example of IVT? Is that accurate, Lily? Okay. My answer is, given the function f of x equals, oh, I don't know. Let's choose x squared plus 7. No, minus 7. Yeah, minus 7. Okay? Now, because we are familiar with what the parent graph looks like, we know that there should be two areas where it crosses over the x-axis, giving us a root or a 0, right? Okay. So we want to, given this function, it'll say use IVT to prove it has at least one 0 on the interval. Let's say -3 to 2. Okay? So what we do is, using IVT, we're going to say that, I'm going to change my color up a little bit here. Alright. So IVT, we just need that it's continuous. So we say since f of x is equal to x squared minus 7, doesn't have any points of discontinuity, yes, this is different from the extreme value theorem. The extreme value theorem simply says that given a continuous differential or a continuous function, that the function will have at least one minimum and at least one maximum if it is continuous. Okay, so now that we've got continuity proved, we are going to progress to saying that f of -3 is equal to 9 minus 7, which is equal to 2, while f of 2 is equal to 4 minus 7, which is equal to -3. What this means is that by IVT, there is at least one value of C between -3 and 2 such that f of C is equal to 0. Because the graph has got to pass through 0 if it goes from the y values of a +2 and a -3. It has got to pass through 0. Yeah, that's all there is to it. Griffin, you didn't learn Rolle's theorem last year? Am I understanding that correctly? Okay, yes, please stay tuned for a Rolle's theorem question. We are going to get to it momentarily. I just have one more of Lily's questions to get to. And Lily, correct me if I'm wrong, but I believe it was talking about an over or an underestimate, right? Okay. So, and I'll change, oh, it's already over there. Okay, this. Ooh, that's very narrow. So the question was, how do we know when when a linear approximation is an over or underestimate? Okay. My answer is that it depends on the function's concavity. Okay? And the visual to go along with this going to give us this, a curve like this, kind of trigonometric, but not quite. And if we take, I'll use this color, a point here, let's call it A, versus a point here, which is point B. The linear approximation at A it'll be something like this, versus the linear approximation at B being something like that. Okay, I'm actually going to redraw that because I think I can do better. That is not at all better. Again, not at all better. Why are you doing this to me, tablet? We were having such a good time before. There we go. Alright, so Lily, if we're looking at, let's see, you can see this little cursor, right? Actually, I can probably change the settings so that it shows up a bit easier. No, you can't see it. Okay. Ignoring that. If we use the yellow lines to approximate a point, and the point is, I don't know, somewhere over here, that point is over the curve. Do you agree? And if the point were to be somewhere over here, it's still above the curve. You still agree, right? Yeah. So in this area, it is concave down. Oops, let me make this smaller. Okay. So at A, the function is concave down. And we have an over approximation. Okay? Versus if we were to look at B, this point is underneath the curve. You agree? And if we look at any other point on this line, say like this one, it's still underneath the original curve. So we say that, again, I'm going to need to make this smaller. At B, the function is concave up, and we have an under approximation. Yes, Chad, that is correct. Looking at your answer, I think you can probably match concave up to being an under approximation, because if up and under both have U's. So if that's a study habit that you do, is you look for little tricks inside the words, that's something that you can look at. Lily, does this answer all of your questions about linear approximation and concavity with over and under approximation? Or estimates? You're talking about the example that I showed you, right? In class? The one you sent me a picture of? Yeah, okay. So, from the example in class, I told you to approximate f of 0.1 given f of 0 equals 1 and f of x equals 1 plus sine x. So what we did was we took the derivative, and I'm going to change colors here so we can see the distinction. Okay. We took the derivative and we got just cosine x. And then this was a point 0, 1. And we're going to use f prime of 0 to figure out the slope at 0. So the slope at 0 is 1. And we used this information. I need a different highlighter than that. There we go. We use this information to create a tangent line. And the way that we're going to do that is we are going to use, not p, y minus y1 equaling m x minus x1. So with our point, this is x1 and y1, and our slope is the tangent slope, which is 1. Plugging this information in, we get that y minus 1 equals x, and so y equals x plus 1. This is our tangent line approximation. All right. So now what we're going to do is we're going to acknowledge that f of x, and we're going to not call it f, we're going to call it like h for the approximation. The approximation function. Okay. So we're going to say h of x is equal to y, which was equal to x plus 1. Now we wanted to know 0.1. So we take that and we plug it in. We have 0.1 plus 1. We get 1.1 as that point. And we want to know, is this point an over or under approximation? Okay, to do that, we need to find the concavity. Of f of x at x equals 1, because that's where we did our tangent line approximation at. And it will tell us if the tangent line we made is going to be over or underneath the original graph. So what we're going to do is we are going to take our, where'd it go? F prime of x is cosine x, so we're going to rewrite that down here. And now we're going to need to take the second derivative of this. The derivative of cosine is negative sine. And we need to put in 1. Right? Now, sine of 1 is something you put in your calculator. But what we did in class is we looked at the graph of sine of x. All right? And my drawing skills are a little bit lacking for some reason. But sine of x. And then sine of 1, this is 2 pi, pi, so That's like 3, 2, 1. So sine of 1 is like here. And we can see that that is positive. Sorry, Lily, I'm only just looking at the chat. You asked where I got x equals 1. Oh, you're right. You're totally right. Because in the beginning, it was the point 0, 1, not the point 1, 0. Yeah, you're right. So all of this will need to go away. Yeah, Chad, so I did the whole little bottom part of this wrong because I plugged in 1 instead of 0. 0 is where we had the point in the beginning. I mistakenly plugged in 1 for whatever reason. Probably just slipped my brain. But I needed to have put in 0 instead to figure out what the graph was doing at 0 instead of 1. So instead of plugging in 1 down here, I need to put in 0. And since sine of 0 is 0, we were like, oh, well, we need to look at where our tangent line would have been. So we needed to look inside here, right? And what we were able to see from looking at the graph is we were able to see that even though, yeah, if you could be black, that'd be great. Okay. Even though sine of 0 is 0 and it doesn't work out for us, if we test a point slightly to the right, which is where we're going to be testing anyway, sine becomes the positive that we know that it should be. Okay, so slightly to the right. Since sine of 0 is 0. Wow, y'all are just on top of it today, calling out all of these errors that I keep making. But the reason being, right? So since we're testing slightly to the right, since sine of 0 is 0, and this is the original sine of x function, right? So since we test slightly to the right, now, so what I'm doing is I'm saying for x greater than 0, sine of x, and I should say greater than 0, but less than pi. Yeah, that's right. So sine of x is greater than 0. And then since sine of x is greater than 0, that means that this means that negative sine of x would be less than 0, because when you multiply by a negative, you have to flip the direction of the inequality sign. So we might not be able to know exactly what negative sine of 0 is, or negative sine of something really close to 0 is, but we know that f double prime of x is less than 0 for x less than pi but greater than 0. So f is concave down. And our approximation was an overestimate. How do you feel about that, Lily? Chad? Oh? What happened? Hello? Are y'all here? Okay. Y'all feel good about the example? I don't know what's going on. Okay, I have no idea why I keep going on and offline, but hopefully it's done. Okay, but Lily and Chad, this over-under estimate, are we good? We Gucci? Okay, Lily, are you ready for a roles example, or is there something that I still need to clear up about this? We didn't say that the second derivative was greater than 0. Okay, so we did not say that the second derivative was greater than 0. Correct. We're not referencing this graph. The only thing we referenced the graph for was for figuring out this part. Okay, so the graph was only for this part. Okay, so I see where all of our confusion is, and I'm going to fix it by just erasing all of this part. Okay, and I'm going to actually draw the negative sine of x graph. Okay, so this is f double prime of x equaling sine of x. Or negative sine of x. Okay, and this is 2 pi, this is pi, pi over 2, 3 pi over 2. The graph is below the x-axis for 0 to pi. That means that the second derivative is less than 0 for x values between pi and 0. Yeah, this graph, Lily, we are just using this to determine when it is concave up or when it is concave down. Okay, so this we use to determine the concavity. Because the sine of 0 was 0 and wasn't telling us anything. So when we came on here and we were like, okay, well, I know that we're going to be testing something that will be just to the right of 0 because we're looking at 0.1. That was down here, and the f double prime of 0.1 was less than 0. It's not concave up, it's down. It's concave up when we get a second derivative that is above the x-axis, which is when it is positive. Okay? This is positive and negative. Up here means that the original is concave up. Down here, the original is concave down. Lily, the graph of the second derivative does appear to be concave up from 0 to pi. But we're not interested in the concavity of the second derivative. We're interested in the concavity of the original function. Yes, we're not looking at how the second derivative graph looks for concavity. We're looking at where the second derivative graph is for concavity. Yes. Because the graph you're going to look at, unless the graph you're looking at is the original function, you're going to do it by if it is positive or negative. So there will be cases where I give you the original function and you can look at the original function to determine where it's concave up or concave down. But there will be other times where I give you the first or second derivative function and tell you to interpret that graph for the original. Correct. Unless it is the original function, you do not pay attention to if it is up or down. Concave up or concave down. Yes, the first derivative tells you if it is increasing or if it is decreasing. The first derivative does not tell you about concavity. The second derivative, you look at if the value of the second derivative is positive or negative. If that value is positive, it is concave up. And if that value is negative, it is concave down. So Lily, are you set? Did I answer your two questions? Okay. Griffin, are you still in the room? You're welcome, Lily. Alright, so we're going to do a Rolle's theorem question. Can y'all refresh me on what the Rolle's theorem question was? Just what is Rolle's theorem? How do we do it? Alright, Griffin, I acknowledge your question. Chad and Lily, do you want me to do Rolle's from the beginning? Or do you just want me to work an example and explain what's going on with it? An example that's different from the example that was in the notes. Okay. Okay. So the question that we're going to answer is, what is Rolle's theorem? And how do we use it? My answer, Rolle's theorem says that any continuous and differentiable function that function on the interval from a to b, for which f of a is equal to f of b, has at least one value c between a and b, where f prime of c is equal to 0. And what that is, if you want a visual for it, it's saying if you have some function like this on the interval from a to b, you would agree that this is a continuous and differentiable function because it is, right? And here, the y values are the same, okay? So Rolle's theorem says that there is some value of c for which there's a horizontal tangent line. Okay? Now, to use Rolle's theorem, you have to prove or show the function is, firstly, continuous. Secondly, differentiable. And then, lastly, that the ending y values are equal. Are you all with me so far? Cool. All right. So, hang on a second. Matt's asking me questions about linear approximation. If he was in stream, he would have already gotten this information, but he's being a little bit difficult. Yeah, calling you out on the stream, Thompson. Chat, are you for real? Alright. So we have to do that, and I was looking for an example before I got distracted by Thompson. Okay. Would you actually need to test for continuity if it has to be differentiable? Yes, because in order to be differentiable, it has to first be continuous. So you have to go through all three of the steps. You can't just assume it's continuous. Alright, so here's the Rolle's theorem example that I found. We've got f of x equal to x squared minus 10x plus 16. Show that the function meets the criteria for Rolle's theorem. On the interval from 3 to 7. Then find the point and Griffin, I'm reading your question. And I agree that if you know that the function is differentiable, then you would know that it's continuous. But we don't know that the functions they give us for Rolle's theorem are continuous until we prove that they are, which I'm going to do with this problem. Okay? I just need to finish writing it down. Then find the point where. Now, because it said find the point, we will actually need to find a point xy where the derivative is equal to 0. Okay, so I see that the stream is down. Okay, so we're back up. I can see everyone now. Okay? Oh, what was the name that you don't know? Okay, so when we're using Rolle's theorem, we don't know that the function is continuous, so we don't know that it is differentiable. Okay, it doesn't tell us that the function is differentiable, so we can't assume that it is, and also, by way of assuming that it's differentiable, assume that it's continuous. Because you know what happens when you assume. Yes, you get thrown into math jail when you assume. So first, let's find out, is this continuous? Well, f of x equal to x squared minus 10x plus 16 is a polynomial with no vertical or with no points of discontinuity. So f of x is continuous. All right. Now, the cheap way that we're going to say that it's differentiable is we want to know that the derivative, what about a rational function? Are you talking about any fractional sort of function? It would, if you have a, so let's say that we have like x minus 4 over x plus 2, x minus 1, okay? This would be not continuous. Yes, Griffin, it does depend on the interval. For x equal to -2 and 1. Okay, but if we were trying to apply Rolle's theorem, we could do Rolle's theorem for the interval of -1 to 0. And then it would be continuous on the interval. And we would be okay. You good, Chad? Yes, -2 to 1, but for Rolle's it does ask to have a closed interval because you do need to have the y values of those points. So yeah, what Griffin said, it has to be continuous at the endpoints. You have to use the endpoints, so you can't do the open parentheses. It has to be brackets. Okay, so the differentiable thing we're going to do is we're just going to take the derivative, right? So f prime of x is 2x minus 10. Again, this is a polynomial, and I'm just going to try and cheat my way through this because I don't want to write all of this again. Coffee and paste. Yes. So this is a polynomial with no points of discontinuity. So f of x, instead of being continuous, now we're going to say is differentiable. And we're going to specify this by saying differentiable at all points in 3 to 7. And we can actually do that for up here, too. All right. So now we have continuity, we've got differentiability. We just need to prove that f of 3 is equal to f of 7. Okay, so f of 3 is 9 minus 30 plus 16. So that is negative 30 plus 25 gives us negative 5. And f of 7 is 49 minus 70 plus 16. 50, 65, and negative 70 gives us a negative 5 again. So f of 3 equals negative 5 is equal to f of 7. So we can now say that all conditions for Rolle's theorem have been met. And we can use Rolle's theorem. Okay? So what Rolle's theorem is going to tell us is that there is some f prime of x that equals 0. It's true, there is one. So we're going to take our derivative function, which was 2x minus 10, and solve it for when it's equal to 0. So x equals 5 is the value for which f prime of x is equal to 0. Yes, x equals 5 is the correct. Yeah, it's not awful. It actually will save a lot of time, especially if you've got a function that you're not familiar with and you're wondering if it's ever got a horizontal tangent. Tan V, yes. X equals 5 is the answer for this problem. Oh, sorry. You remember when I said up here that we would need to find the point, and I even highlighted it all? So I've got to find the point. So we've got x equals 5. Now we have to plug in. So we go back to f of x, which was x squared minus 10x plus 16. We're going to plug in 5. So 25 minus 50 plus 16. So negative 25 plus 16 is a negative 9. Right? So our final answer is 5, negative 9. Hey Matt, welcome.